let's talk a little bit about the normal distribution and how well it kind of works. So a reminder about just the normal distribution, it's one of the most common shapes. It's that nice, beautiful bell curve that we see. So it's not skewed, it's not too peaked or too flat, it's that nice, beautiful bell curve. That just happens very, very often in statistics. If you haven't seen the video about the normal distribution and sort of how it relates to standard deviations, go watch that one first. But sort of continuing on about how we can use the normal distribution and kind of how well it works. If we are to take a random sample from a normally distributed population, so assuming that the population has that nice normal distribution, even if we're taking really small samples, it's still going to give us an approximately normal distribution. And so this is one of the major components of what's called the central limit theorem. And this is something that holds true when populations are normal. But also if they're a little bit off of normal, this still holds true, and this is still part of the central limit theorem. And so if the population itself, so remember, when we're talking about inferential statistics, we're trying to take what we find in our sample and apply it to the larger population and sort of be able to discuss the larger population, either that we drew our sample from or that's similar to the population we drew our sample from. But if that population is a little bit skewed, so the population itself is not that nice, beautiful, normal distribution, it's a little bit skewed one way or the other, then if you get fairly large samples, you're still going to tend to produce at least an approximately normal distribution. So this central limit theorem holds true when populations are normal or if they're like approximately normal. So this is if we're not too far from normal. So we're still being able to use those relationships between standard deviation and sort of the proportion of the population that should be within 1 standard deviation, within 2 standard deviations, and 3 standard deviations of that mean. So it's still working, even if the population is a little bit off normal, a little bit skewed. However, what if the population itself is not normal at all? What if it's very skewed, or what if it's very leptokurtic or platykurtic, or what if it's just not normal? Well, what kind of error are we going to make if we assume normality when it's not there? Interestingly, even in cases of extreme asymmetry, so even when we have really big skews and we are not that nice normal population that we're kind of assuming, still about 75% of the data are going to fall within that plus or minus 2 standard deviation. So that's not as high as the 95, absolutely, but it's still fairly high. And about 90% of data is still going to fall within the plus or minus 3 standard deviations. So it's not that 99% or the actual 99.74%, but it's still fairly good. So it's a lot of error. We know that. But it's not so bad that standard deviation is actually totally unusable. So if we use one of these distributions thinking it's normal when it isn't, there is a lot of error. But it's not so extreme that we can't still use those standard deviations and that they don't still tell us something important. So even in cases where the population isn't normal, we can still use standard deviations to help us figure out where the majority of our population should be. So some other common distributions that we see that are not normal, and keep in mind that these don't have normal curve properties, so we can't use standard deviation with them, and we wouldn't even try. And it's not like the central limit theorem where you would be like, oh well, it's close enough. No, these are like not normal at all, not even close. So we wouldn't use the standard deviation properties. And of course, I had to put a Mark Wahlberg meme in there saying, "Sup, girl, that non-normal distribution's got me questioning my assumptions," because that is so statistically relevant, and it's always relevant to have Mark Wahlberg. So some examples of some other common distributions that are not normal, and again, so we would not use standard deviations with them, is uniform distribution, the negative exponential distribution, and the logarithmic distribution. So here's what the uniform distribution looks like. It's literally just like a straight line across as far as your range goes, because it's uniform. It literally, all scores have the same number of cases in it. So if, for example, you had a sample that contains one person of every age between age like 12 and 80, you would have a uniform distribution. It would be straight across. There is the same number of people at every possible score. That's a uniform distribution. So you can see why we can't use the standard deviation properties anymore, because the mean would just be like in the middle, even though everything is all the same. But you wouldn't have a certain proportion of your cases within standard deviations. It just doesn't work if you have a uniform distribution. So then the negative exponential distribution looks like this. And so essentially, it's this negative relationship where as x, so x would be on our horizontal axis here. So as x goes up, y goes down. So this is our y-axis. So as we go up in our x, the y is dropping. However, it is not a straight line. It drops faster at lower values of x. So you have this drop here, and then it kind of sort of flattens out a little bit as it approaches the y-axis. So this is most commonly the type of curve you would see in what's called a survival curve. And so, for example, if you look at if offenders are released from prison, we can talk about offender survival, meaning how long they can stay out before they reoffend and they're put back into the system. So we talk about offender survival, meaning how long can they survive without recidivating. You look at, so if this is our release time, and our x-axis is time since release, you would have, into the community from a prison, you would have this precipitous drop at the beginning where you have a bunch of people that like reoffend basically right away or shortly after. And then the longer the time gets out from the time of release, the less proportion of your population at any given time is going to end up recidivating. So the cumulative effect is still like, there's like, by the time you get out here, if you actually had a survival curve that almost approached the y-axis, basically everybody fails. But at any given time, the likelihood is going down. So that would be the sort of where you would see that most often. Although survival curves are also literally when you're looking at people surviving diseases and stuff like that too. But from a criminological perspective, the offender release is the best kind of example. So then the logarithmic distribution, it kind of looks like this. It's almost the opposite of sort of the survival curve, where this is now a positive relationship. So as x goes up, y goes up. So there's a general trend upwards here. But again, it's not straight. You have this faster rise at the beginning at kind of lower values of x. So it's kind of like the same as the last one, where you have this precipitous, in this case, increase instead of decrease, and then it kind of flattens out. So it's kind of the same idea. And for fun, this is what a sine wave distribution would look like. And so y does have a patterned increase and decrease and so you would see that the x values, the x bar here is kind of in the middle. And so y does have a patterned increase and decrease as x scores go up, but I don't even know when you would see that, but it's an interesting pattern to see.